Okay, so this lesson on 3.1 is kind of the basics or introduction to graphing exponential functions. So at the end of the video, you need to be able to graph exponential functions using transformations, and you can talk intercepts and asymptotes and kind of those critical values from that, as well as using a couple formulas that come up in 3.1 when we talk about different word problems. So on this first example, we are just looking at the parent function, y equals 2 to the x. For any exponential, your parent function is going to be y equals b to the x, where you have some base value. In this case, it's 2. And if we plugged in a bunch of values for x and y, usually we look at -2, -1, 0, 1, and 2. Anytime you plug in 0, you're just getting that base value. And anytime you plug in 1, sorry, I said that wrong. Anytime you plug in 0, you get 1. Anything to the 0 power is 1. When you plug in 1, you're going to get that base value. So on this function, 2 to the x, when I plug in 0, I'm going to get 1. And when I plug in 1, I'm going to get 2. And that's actually the table we'll start with every time. I'm going to add a couple more points just for this first graph. We won't usually do these. If I plug in -1, 2 to the -1 is a half. If I plug in -2, 2 to the -2 is a fourth, and 2 squared is 4. So I can plot a couple points here. -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. So you can start to see the shape of our graph. But again, when we use this parent function, these are the 2 points we're going to focus on all chapter. Okay? A couple other things I do need you to notice. We have an asymptote here. You will have a horizontal asymptote at y equals 0. That's part of your parent function. It can shift around with your transformations, but that should be noted. No matter what x values I generate here, I could never get a negative. I could never drop below this. So it would flatten out. It would get really, really close to 0. Notice that a negative exponent creates a fraction, so your fractions would get smaller and smaller and smaller, but they never would become negative. So you have this horizontal asymptote here. As we talk parent functions, we could say that our domain here is all reals. We're going -infinity to infinity. Whoops, infinity. Our range here would be, oops, we're not equaling 0, 0 to infinity. So you can see all x values, all reals. Domain is 0 to infinity, but we don't actually equal 0. That's our asymptote, so that's why this is a curved bracket. Okay? If you asked for x and y intercepts, your x-intercept would always be none because that's where our horizontal asymptote is. And your y-intercept, if you plug in 0 for x, our y-intercept here is 1. So those are some critical values that we can look at as we do transformations. So if we take a look at number 2, we're going to start with our parent function table. So in your parent function, we would look at the ordered pairs 0, 1, and 1, 2. Our parent function is y equals 2 to the x. We would have a horizontal asymptote at y equals 0. So that's everything in the red boxes up above. If we look at this transformation, because it is with x, it is flipping our x values. So this would be a reflection across the y-axis, or you could tell me that you are flipping your x values. So I'm going to multiply my x's by a -1. 0 times -1 is still 0. 1 times -1 is -1. So my order pairs become 0, 1 and -1, 2. When I multiply that, nothing changes because it's at 0. So my horizontal asymptote is still the same. So now my graph looks like this. What I need you to know about an equation like this is that this is exponential decay. The first problem was exponential growth. If x is positive, if that exponent is positive, that's exponential growth. And as soon as that exponent flips, it becomes negative, so now you have exponential decay. That's important to keep in mind as you think about the shape of your graph. If you need more points, then plot more points, but those are the kind of the 2 basic points I must see. And most of you, once you draw in that asymptote, you can see how your graph would slope down and level off with the asymptote. So that should be enough really to get your graph for number 2. Domain is still all reals, range is still greater than 0. So you can see that on your graph. Number 3 has some more transformations involved. What I do want you to notice is that your parent function has not changed. If I remove any multiplying and dividing, any adding and subtracting, my parent function is still 2 to the x. So the table I'm starting with is 0, 1, and 1, 2 from my parent function. This is always your base, remember, on that exponent. And my horizontal asymptote is starting at 0. Then we do our transformations. If you think order of operations, we're going to start with this. That transformation is going to make us go 1 to the right. So when I go 1 to the right, this is now at 1, this is now 2. If I slide my horizontal asymptote left and right, it doesn't move. Next thing in order of operations would be that this 3 here creates a vertical stretch. So I'm going to vertically stretch by 3. So that gets multiplied by 3, and that gets multiplied by 3. Horizontal asymptote times 3 still hasn't changed. Last transformation is that I'm going to go down 4. When I go down 4, this becomes -1 and this becomes 2. And your horizontal asymptote, if you take a horizontal line and move it down 4, we would now be at -4. Make sure to graph that horizontal asymptote. It helps you see where your function is going. So I am at 1, -1, 2, 2. You should be thinking this is exponential growth, so it should be sloping up. If you think about connecting the dots here, it kind of looks linear with only 2 points, but it's not a line. Remember, it's exponential growth, so it's going to level out with your asymptote and then explode up like exponential growth. So I'm starting here and then moving up for exponential growth. If you talk domain and range, our domain here is still -infinity to infinity like always. Our range this time, since I went down 4, my asymptote is at -4, so now my range would be -4 to infinity. And then if you talk x and y intercepts, the values, don't look at that right there because that was just kind of an estimate as I drew my curve. The values take a little more solving. So you could find the y-intercept because you could substitute for 0. If you are looking for an x-intercept, you have to solve that equation, and we'll do that later this chapter. So this one, the intercepts are a little bit more work. You could do it on your calculator, but for now we're going to kind of leave that alone. The next idea with exponential growth and decay is that you need to be able to calculate some word problems. So one of the big things we talk about with exponential growth and decay is investing. When you see this formula, I can tell you first that you'll need to memorize it. Think about how exponential growth works and how interest rates work. So your R is always going to be your interest rate. Know that it's an annual percentage rate, so that rate is over the course of the whole year. But if we're going to compound monthly, you're going to calculate interest every month. So you're going to get interest 12 times over the course of the year. So this interest rate is getting divided by 12 because you're not going to get the whole 2.5% every single month. The 2.5% happens annually. So you get 2.5% every year, so that's why you get divided by 12. So the n is going to be the number of times you compound. That's also this n. It's added to 1 because you're growing. So if this was just 1, that'd be like 100% of your money you're getting back. But since we're growing, we're going to get more than 100% of this money back. So that's why it's growing. P is your principal. That's your starting amount. Value. And then T is obviously your time. That should be in years because we are talking about an annual interest rate. So as I said at this equation, I would say we are starting with $9,000. We invest that in an account for 5 years. So it's going to get interest 0.025%. 2.5% is 0.025. That's an annual rate. If we're going to compound monthly, we divide it by 12. So we're getting 1/12 of that every single month. And we compound interest every single month for 5 years. So I would get interest 60 times if you do it 12 times a year for 5 years. That'd be 60. So that's why your exponent becomes 60. You can type this straight into your calculator. You shouldn't need anything fancy. So you're just doing 9,000 times 1 plus your interest rate over 12. And then your exponent needs to have both the 12 and the 5. You shouldn't need parentheses. It should stay up there. And then you get the amount in that account. So after these 5 years, our bank account would now have $10,000, $197 and a penny. If you care about your rounding, if we're talking about money, make sure you round to dollars and cents. When you compound continuously, that means it's compounding faster than every second. It's always compounding. So then it uses the PERT formula. P is still your principal, like up above. R is still your rate. E is a number. It's kind of like pi. If you look in your calculator, it's above the natural log button. So you can see it here, second ln. So if you want to know what E is, you can do e to the first power and see that E is about 2.718. You don't really have to know that. You'll use the E in your calculator, okay? But long term, that's going to come up this chapter, okay? So when we're compounding continuously, we use this formula because you don't have an n value, so you couldn't use the formula up above. So if we compound continuously, we are investing $9,000. We are compounding continuously. Our interest rate is 0.025. And again, we're doing this for 5 years. So that's what your formula would look like. You can type this in your calculator all at once. 9,000, get that E, second ln. And then your exponent is 0.025 times 5 years. So now we would have $10,188.34 if we round appropriately. The last problem asks you to find the initial amount and the amount after 30 years. If your radioactive element given by this formula, and T is the number of years. So here's your formula. An initial amount means no time has passed. So for your initial amount, you are saying y equals 10 times a half to the 0 divided by 29. 0 divided by 29 is 0. Anything to the 0 power is 1. So your initial amount is 10. That's how your formula is set up. Think about your p-value here and your p-value here. Your initial amount is like that coefficient, that lead coefficient. So this should be your initial amount in exponential formulas. So then if we look at your amount after 30 years, since we know t is the value in years, we can now say y equals 10 times a half, and then 30 is what goes in the numerator of that exponent. So I'm just going to type this straight in my calculator, 10 times a half, and then my exponent is 30 over 29. Make sure that's all in the exponent, or use some parentheses there if your calculator doesn't look right to you. WebAssign will tell you what to add. I'm going to do 2 decimals this time. We have 4.88 for our answer there. We will do more of this in class, but that should get you started on 3.1.